get a better introduction this evening, I guess. And again, everybody here better show up. I'm going to be taking notes. But most interestingly, most importantly, perhaps, is he's the lead author on, I guess, Chapter 9 of the IPCC, most recent IPCC report. And he's a true expert on ocean science, oceanography, climate, so on. So,
thank you very much. Hi, everybody. So, yeah, I guess I will. So I'm in an Earth Sciences department, and I used to be here at the University of Colorado in the Atmosphere and Ocean Sciences department, but I started out in physics, so some of the pieces are linked up. Although, as you'll see, I think the primary job I have today, both in this talk or this series of 3 talks and tonight, is to try and convince you that there is actually a straight line from the kind of things we're talking about all the way up to climate change on a societally relevant scale. And so we'll do the more mechanistic, detailed side in this series of 3 talks, and we'll do the kind of hand-wavy, big picture stuff tonight. But you'll see that it does actually link together. Where I'm trying to go is to get you to the point where it all makes sense, that there is a way that there is there, but also to really highlight the opportunities for folks in condensed matter to contribute along the way. There are big parts of this story that we still don't understand. And I think what we have been able to do at this stage is just to highlight that those fundamental uncertainties actually do cascade all the way up to the end story of how much warmer the Earth gets under a particular carbon emission scenario. So that's where we'll get to in the end. But for now, I want to talk about a kind of phenomenological piece, and then what is the ocean like? You know, there are about 10 to the 9th scales of interesting fluid motion from the oceans, from the global scale down to the Kolmogorov scale, and about 10 to the 8th of those are turbulent. So we have a wide variety of different kinds of turbulence. We have the great advantage that we can observe all of them, you know, to some degree or other. And so we have a lot of information about all those different scales and a lot of knowledge about scale by scale by scale by scale, how the dominant dynamics vary. What's the harder problem is how those scales interact, particularly over long distances. And so that's where we're trying to get to. But I want to talk fundamentally first about the equations that we use, where they come from, and how we make approximations or choose not to make approximations based on how computationally expensive those different equation sets are. So I'm going to talk a little bit today about that. And there is a review paper that I wrote when I gave a similar series of lectures in Mallorca 5 years ago. That's one of the ones that I included on Slack, which is Notions for the Motions of the Oceans. And so that's a fun kind of survey across this. And then there's also challenges and prospects in ocean climate modeling, which tells you really what the latest up-to-date challenges are. And that's kind of another review paper, which is led by me, but co-authored with a whole mess of ocean modelers from all over the world. And then there's another little short nature commentary about, do the small scales of the ocean hold surprises? And so that's a short piece which talks about some of these key issues and why, you know, we'll continue to push to higher and higher resolution, but that's not going to be enough to solve the problem. But I think that'll become very clear over the course of these 3 days anyway. Yeah, it's similar. We're not going to talk about surfactants, but yeah, sure, the motion pollution to the ocean. Well, I could say the Gulf of Mexico research project, one of my funders here actually is BP in disguise. After the oil spill, they funded a lot of oceanography. So yes, so that's, I guess, the motion of certain kinds of oceans in the oceans. Okay. All right, so the ocean is vast and diverse. This is true of both turbulence and waves. And I know you've been hearing about topological waves some. We'll point at some of those pieces. But I want to show you in a space-time diagram how that all breaks down. And then where we want to get to are what the breakpoints are in transitions in phenomenology. So like Feynman, the nice Feynman quote from Nigel's talk, when does qualitatively different behavior start to accumulate? And why, and how do we anticipate where those are? And if we went to a different planet other than Earth, would we be able to guess where those transition points are? That's an important part of the question. And then I'm going to focus on 3 different characteristics of turbulence: the mesoscale, the submesoscale, and boundary layer turbulence. And that's because those are really important ones for this climate story that we're telling on the big picture. And you'll see how those fit. And then today's work, our business piece, is to go from the Navier Stokes equations to touch on how the Boussinesq approximation works, whether or not we can be hydrostatic, on which scale we could be hydrostatic, whether quasi-geostrophy makes sense for this context. And then the last piece, the wave average equations, which is kind of a weird thing, which is it looked like it was an obscure single scale approximation that was really useful for boundary layer turbulence. But if we have enough time, I'm going to show you that it actually does more than that, which is kind of fun. Okay, so first off, let's cascade from the global scale down to the smallest scales that we've simulated, which is all of the scales. We can't do it all at once, but let's take a look at each scale. So this is showing surface speed on a global scale. This is from a high resolution simulation, the LLC 4320 model, which means the latitude longitude cap with 4320. So this is a polygonal Earth with 4320 polygon shapes on each direction. And so it works out to about 2 kilometer resolution over the whole globe. And you can see there are all these little wiggles in speed. Some of them are attached, like the Kuroshio and the Gulf Stream, to a particular place. I forgot I was supposed to be pointing over here. Some of them are attached, like the Kuroshio and the Gulf Stream, to topographic features. Others out here are just kind of in the middle doing something interesting. There are these pulsations. Does anybody want to guess what the pulsations are of this out here?
What's the time scale?
There's a little clock.
Yeah.
Oh, let me restart it. What are those pulsations, you think? So those are hours ticking by, day, about a day every 2 seconds. Anybody guess what those are? There are tides in this model. There's a signal of the tides in the tidally dominant region. This is actually storms. So that's wind-driven surface response to storms by going over top. And they are located in the storm tracks. Okay, cool. So that's what a simulation, a high resolution simulation of the Earth looks like, at least in terms of speed. But let's zoom into this little blue box. So, and first I will pause to tell you that one eddy, the mesoscale eddy, is 1 to 10 Rhode Islands in size. So if you teach in Rhode Island, all Rhode Island is the standard metric. So that's the scale of what you're thinking about. I didn't used to have this slide, and then I was giving this related talk, and my wife said, I thought those things were like tabletop size, not the size of a state. But the big ones are about that size, 100 kilometer scale. Okay, so we've zoomed into the little blue box into the South China Sea. And now we can see these features now. This is actually temperature rather than surface speed, which is a little different, but you get kind of phenomenologically the similar feel. Now you can really see the tides that are transitioning into internal waves as they propagate up on the shelf toward China and Hainan Island down there. And you can see there are these big sort of frontal features. There's a nice one right there, which is a cold water next to warm water. And then there's all this little small scale stuff. The black dashed lines are indicating where the topography, the bathymetry is changing. So it's shallow water over here, deeper over here. Okay, let's zoom into that box. Now we can't zoom into that box in this same model. We've run out of resolution. But we can start another model at higher resolution and make it about the same dimensions as that box. So now this one is giving us temperature again at the surface. You can see there's a lot more small scale variability. And this is just a front, warm on one side, cold on the other in the channel, which makes our life simpler. If we go a little deeper, 200 meters depth, we only see the big eddies. We don't see the little eddies. So there's something special about the surface that's leading to those smaller eddies. And I'll give away the hint right now. These are mesoscale eddies. Those are submesoscale eddies. So the mesoscale spans the full depth of the ocean. The submesoscale is trapped in the upper boundary layer. And this is a side view. And now we can see the upper boundary layer. Play that again. We can see the other upper boundary layer, which is being mixed every night by cooling and convection. That's why it doesn't go away. And you can see that it might be vertically uniform across that boundary layer, but it's certainly not horizontally uniform in temperature across that boundary layer. In fact, those horizontal surfaces are getting propped back up every time there's a mixing event. So that surface mix layer is going to be key to our whole story. And it's the place where the submesoscales live. But the submesoscales, obviously, those little eddies are growing on the edges of the bigger eddies below. So you can see, like, on the edge of this feature, you can see the submesoscales are getting produced. So there's a transfer of energy across scales from the potential energy that's being caused by these large eddies straining the temperature field into the smaller scales of the submesoscale. That's something we're going to talk about next time, is how to diagnose those kind of scale-to-scale transfers. Oh, forgot to show you the box. Now we're going to zoom into another box this size. Okay, now we're talking about 20 kilometer by 20 kilometer domain. This is another idealized calculation. We had to leave that one behind, start a new one. So this is 20 kilometers by 20 kilometers by 150 meters depth. And you can see now there's two fronts. The wind and wave direction is singled out because on this scale, the wind and waves really have a lot to do with the dynamics. This is showing temperature from above and then temperature on average from the side. So this is like a mirror reflecting the depth properties. And again, we see the mix layer. We see submesoscale features in the mix layer. And then we see interesting, even smaller scale features that are breaking off along those fronts. And so it's not clear what those are. There's also a strong asymmetry. It goes from cold to hot to cold, and then it's actually a periodic domain. Why is that one stable and this one unstable? Has something to do with the way that the wind and waves are interacting. That's the kind of thing we'd be wondering about. And we'd like to know more. This is just the temperature field, but we'd like to know what's going on with all the mixing that has to do with that. So we zoom in again to this little box in the same simulation, actually. And now we're coloring temperature again, but I'm not coloring all of the domain now. I'm just coloring the locations of large vertical velocity. And so these are each downwelling jets. And then apparently this large front between cold and warm has a strong downwelling feature in it. And you can see that there's converging flow into that front. And there's a lot of interesting stuff going on. And now we can see that these downwelling features are all lining themselves up in the wind and wave direction, which is kind of interesting. That's what we'll get to at the end. I'm not talking about that. And this is now only about a day of simulation that we're seeing evolving over this time scale, whereas before we were running by over a good fraction of a year. And it's qualitatively extremely different kinds of turbulence from what it was on the largest scales. In fact, on the largest scales, the vertical velocity was negligibly small in comparison to the horizontal velocities. At this scale, the vertical velocity is larger than the horizontal velocities. It's not isotropic anywhere in 3D until we zoom into another box. And now, this is not my simulation, not of these, but this is one showing salt fingering, which is what happens when you put warm, salty water above cold, fresh water. It's still convex, even though there's no density difference. Or you could actually have the density difference be slightly stable and it will still convect, because there's a difference in the molecular diffusivity of temperature and salinity. And so eventually we get to a scale where we start seeing the molecular diffusivities mattering in the classes of turbulence. And that's this tiniest scale. And then beyond this, we don't worry too much anymore. Does that make sense to everybody? And I don't have any scales in this. This is not my movie. I have no idea what the scales are, but I would guess this is about a maybe 10 centimeter by 10 centimeter box. Okay, so we just ran through in videos from the global scale, maybe not that long of a time frame. Didn't show the continents moving. That's a longer talk. Down to the finest scales that we thought we were worrying about. So let's take a look at the space diagrams. We have length scale here along the x-axis, time scale along the y-axis. We have Earth's circumference over here. We have Earth's age up there. And then we have 1 centimeter and 100th of a second down there on the bottom. What are all these little weird lines? So we said that, so up here, this is salinity diffusion, temperature diffusion, viscosity. That salt fingering effect is close enough to these that it actually can sense the difference. A lot of other stuff is far away from those in this kind of Kolmogorov regime where we don't expect the specific diffusivities and viscosities to affect the flow. That's where all this action is over here. This isn't everything. These are just the things we tend to put names on, I should say as well. But some of these things kind of are a good sense of where everything is. These boxes are roughly showing turbulence. And then out here, you get to things like El Nino and the meridional overturning circulation and the gyres. Those are large advective phenomena. So there's some kind of slope here that's giving us what a sense of the typical energy distribution is or velocity scale as we go across. It's not quite a one-to-one, it's a little bit shallower. And then the mesoscale, which I don't even have a box for because it kind of messes things up, would be somewhere in here. So those big eddies that are the size of Rhode Island is somewhere in here. These are the inertial oscillations, which is what the Foucault pendulum over there obeys. That's the time scale of that. And we can see that the submesoscale eddies are really pushed up against the inertial oscillation scale. They're really sharing that time scale of about 1 over a pendulum day, 1 over f. Okay, so the advective scatter of stuff is along here. These are all dispersion relations of different kinds of waves. Sound waves down here, really, really fast. We're going to come back to that. Tsunamis or long gravity waves, capillary waves, Rossby waves, barotropic and baroclinic, Kelvin waves, which is one of the things that got a lot in the topographic wave discussion, cutting in here and then matching off into the inertial oscillations. You know, this is the regime of the topological waves part of this diagram. That's where it's all happening, where you're bumping against this inertial oscillation. And either you have gravity waves on one side and then semi-balanced waves on the other side. Let's see what else have we got in here. Oh, these vertical lines are the sizes of different ocean basins. Here's the Mediterranean. It's hidden there, but that's the Pacific, the Atlantic, the Southern Ocean, the Indian Ocean, the Arctic Ocean. This is the mean depth of the ocean, somewhere over there. So you start to get a sense of where things are. So where do you think a climate model sits on this diagram? Should be. Does it though? It can't. We can't reach the bottom over here in length scale. Our grid is too coarse. We can't reach the bottom down here in time scale. So in fact, our length scale cutoff, our time scale cutoff is right around here, around 10 to the 4. That's about a time step for a climate model. And our length scale cutoff is around 100 kilometers. So right here. So climate models really just do this part of the diagram directly. And that simulation that we saw went from 2 kilometers. It was kind of over here a little bit, but actually it didn't go very far that way. Why do we need to go that way? What's on the top? Really, really low frequencies, right? Things like the Milankovitch cycles of change, which is what drives the transitions from ice ages. And climate change is on a 100-year time scale, roughly. So it's up in this territory. So we need to go that way to get to climate change. We need to go this way to get high frequency stuff. We need to go that way to get high resolution. We need to go this way to get the whole Earth in. We're trapped in what we can do. And so one of the concepts I want to put in your brain is the concept of a teragrid, 10 to the 12th grid points. So 1,000 by 1,000 by 1,000 spatial points by 1,000 time steps. That's a pretty reasonable calculation. All of you could garner that much computation without much work and run a model that did that. So if we start thinking about computations in that scale, that's a useful piece. A climate model is typically 40 or 50 of those for a single simulation. And so you can keep that in mind as we go along. Okay, so why is it a problem with these small scales? Well, so we get down to the 100-kilometer scale. Maybe we sometimes have those eddies included, maybe sometimes we don't, depending on the model, specific model we're using. But there are these sharp fronts and eddies, the submesoscale piece, that are ubiquitous in the world's oceans. Everywhere we look, we find them. Except they're quite different under sea ice, which I'll also talk about. But as well as features such as shelf seas, we saw where it transitioned from turbulence into the tides as we went up onto the shelf. And under ice shelf cavities. So, you know, the big ice sheets in Greenland and Antarctica, occasionally, especially in Antarctica, go out over the ocean a little bit. And there's a floating ice shelf, it's called. And that ice shelf is thought to buttress the ice sheet behind. So if you lose the ice shelf, the ice sheet starts dumping out quickly to fill it back up again. We care an awful lot about the ice sheet, which is grounded and sits on the ground, because if it melts, it adds to the mass of water in the ocean and leads to sea level rise. The ice shelf is floating, so we don't actually care if it melts on its own, but if it releases that ice sheet by breaking off, that's a big problem. And what controls the release of that ice shelf is melting underneath by warming oceans. So we don't have that in climate models right now. That's something we would very much like to resolve. These small scale processes can play a key role, how the large scale ocean cryosphere evolved under climate change, possibly posing a challenge. That's exactly the challenge we're talking about. So how challenging is the challenge? Well, we can say, oh, there's Moore's law, this, that, the other. It's even better to just do a literature search and go back in time to the first IPCC report, up to the 6th, and pay attention to what resolution their models actually were. There's a lot of socio-cultural, economic aspects as to how big of a computer you're willing to buy for climate change studies. That's part of this. Plus also Moore's law, plus also complications in switching from few processor machines to massively parallel machines and the consequences of that, and did the software keep up? Plus, we actually are making our software more complicated. We didn't used to have an active ocean in climate models. We had a slab ocean, which was just kind of a hunk of mass at the bottom. So we add oceans, we add biogeochemistry, we add aerosols in the atmosphere that makes it more complicated. So the software is getting more expensive, even as the computers are getting fast. So this is the net result. The median of these goes somewhere like this. If you just pay attention to the finest resolution ones, which don't have a lot of those extra add-ons that I was just talking about, you see a pretty nice exponential. So this is a log linear. So an exponential increase in resolution or increase in refinement of the finest resolution going like this. And so those big eddies, those mesoscale eddies, hey, even this round, we actually got to mess the models that were in the permitting zone. If they were down here on this end, we would say they resolve all the mesoscale, but in there, they've got some of those eddies, maybe not over the whole world. It's actually easier to resolve them near the equator. That simulation we zoomed into is down here, so it's doing pretty well. This is the range you would need to be to resolve those submesoscale eddies. This is where the ice cavity models tend to sit, the ones underneath the ice shelf. This is the boundary layer where we started to see, and then even a little bit farther down would be those salt fingering models. So if you want to branch out this way, when are we going to get to boundary layer resolving models? Sometime around 2100. When do we get to global ocean DNS? Around 2200. So from the climate change perspective, that's too late. 2200, we're already well into climate change. Even 2050, you might say we're well into climate change. So we need to do something. We need to think about a different approach. Okay, so we can do this with nesting and overlapping, like I was just explaining. We can pop teragrid scale models together, and we can get from the top to the bottom about 4 or 5 of those. It's an accessible amount of computing. If a simulation spans more than one scale, you might need 10 to 100, 10 to 1,000 teragrids. And so we'll see some bigger calculations. A few of those I showed were actually much bigger. And that's nice because then you can talk about interactions between adjoining scales, all in resolved dynamics. Okay, so, oops, I missed my little, what equations do we use at each of the nesting scales? Any ideas? We keep saying everybody knows these equations, so which ones are those? We got Navier Stokes, right? Is Navier Stokes the right set of equations to use? On some scales, on that smaller scale, maybe. But as Nigel nicely showed, the viscosity drops out a lot of dynamics on larger scales. So we'd like something that's not Navier Stokes that allows those small scale effects, surface roughness, turbulence of the bottom boundary layer, works a lot like Nigel was describing this morning. That should be part of the larger scales, so we don't have to bother to resolve that viscous boundary layer at the bottom of the turbulent boundary layer and so on. And we just talked about how those eddies are missing, and those under ice shelf eddies are missing. So we've got a lot of work to do to bulk parameterize those effects when they are not resolved. And each simulation scales has a different set of parameterizations because something different is unresolved at each nesting level. So we have the equations of fluid motion, which if we could resolve everything, we could do global ocean DNS using all of Onsager's stuff, and we could do that in 2200. And then my joke is we're immediately going to start trying to wonder about what would happen if we use the kinetic theory rather than continuum mechanics, which I'm sure we will do. That will be fun. That's my prediction. As soon as we can resolve the whole world with continuum mechanics, we won't be happy with that. But anyway, okay, so we don't know how to solve them. So here's that same cluster of models, and now we zoom out a little so we can see Euler and Laplace, Navier Stokes. Those were the years those equations were invented. The ocean model resolution would have been only one grid point, not even on the Earth back then. But if we go to the front, 2200 is about when we hit global ocean DNS, and those equations become relevant. Cool. All right. So understanding each scale is needed, as we can't afford to resolve all the scales at once. At each grid resolution, we need to parameterize the smaller scales, which is subgrid modeling, parameterizations, lots of different words for it depending on the community you're in. Fronts appear at each scale with varying intensity. That's a nice sort of hook to hold on to, is what, if you understand how the fronts happen in each scale and the instabilities of fronts, it actually carries you pretty well along that whole range of scales. And then what equations are appropriate. Okay. And this is sort of the topic of this Notions for the Motions of the Oceans chapter that's going through this. Okay, so one way you can do it is you can reduce models. You can throw things out of the Navier-Stokes equations and Keith's discussion of the stuff that he talked about, whatever, last week, whenever that was, down here. And then parameterizations on this side. So now we're adding things back in. So we're inventing new equation sets where we've thrown out things that are inconvenient and then added them back in a different way is the game. And these numbers are not whatever 18th and 19th century numbers. These are last year or this year. Okay, so that's the way that we are approaching this problem, from this kind of brute force approach. Now, in the end, I'm going to surprise all of you by saying this is actually not the right way to model at all. We should use a simplified dynamical system that we can use machine learning style approaches to emulate the behavior of a big complicated model and actually do something really clever. But cleverness is in short supply. Brute force is, you know, what governments are willing to pay for. Okay, so here we go. So how do we decide what's missing at each scale? Well, we go to the grid scale, or whatever the finest Fourier mode. It doesn't matter what your discretization method is, but you've got a discretization. We go to that discretization and we evaluate our dimensionless parameters there, and we say what's going on. Grid scale Reynolds number. These little asterisks mean as resolved at the scale being used in the model. So we might not use the viscosity of the real world. We might crank it up just to make the model stable. So that's what I mean by this viscosity star. Grid scale Rossby, I'll come back to that in a second. Grid scale Richardson, grid scale Peclet. So Richardson number is the competition between stratification. So the oceans are stratified. They're more dense at the bottom than they are at the top. And shear. So the shear part is trying to mix it up, and there's a missing, no, it is not. Okay, and so the stratification and shear are in competition. The stratification is trying to damp the turbulence the same way that the sand did in the same storms, because you push down light stuff into dense stuff, and it requires production of potential energy to do that. On the other hand, the TKE is trying to mix. So Richardson number gives you the balance between those two. Rossby number is talking about the rotation of the Earth versus the vorticity of the fluid. So when the Rossby number is small, the vorticity in the fluid is small on that scale. This is a scale-dependent quantity compared to the rotation of the Earth. So, all right, here's a quiz question. Is the Rossby number small or large for ocean motions? Which ones? Small on which scale? On the gyre scale, it's very small, order 100th, maybe 1/10 for the mesoscale, order 1 at the submesoscale, order 1,000 in the boundary layer turbulence scale. So it depends very sensitively on where you are in that cascade of different regimes. And then the Berger number is a really important one for the mesoscale, which is actually a product of this one and this one with some fiddling. And it measures the ratio of the grid scale to the Rossby deformation radius. The Rossby deformation radius of the full depth ocean is a useful kind of fixed point in a rotating stratified system. It's where the rotation and the stratification both work in kind of the same magnitude to set the instability scale right there. And so those mesoscale eddies occur near the Rossby deformation radius. And so the Berger number tells you how close you are to the instability scale at your grid scale. So if your Berger number is, let's see, small, it means that you don't resolve those eddies. If your Berger number is big, it means you resolve those eddies. Okay. Yeah. Yes. For linear stability, we can always reduce it by reducing the time step. Yes, that's true. It is. Yes. There is a spurious linear instability that occurs whenever you have these damping pieces too small, and it is both in the linear piece and the nonlinear piece. So you can reduce the time step and make it more stable, but once they do grow finite amplitude, then there'll be a nonlinear instability that takes over, and they'll be undamped, and you won't get the right energy flow through the system. Yes. Right. So the three ones I want you to keep in your brain are the mesoscale, the submesoscale, and the boundary layer turbulence scale. The mesoscale is the one near this deformation radius. It's around 100 kilometers, in 10 to 100 kilometers globally. The submesoscale is almost the same calculation, but it's based on the deformation radius only of that upper boundary layer. And this deformation radius actually is proportional to depth. So it's about 40 times smaller just by being trapped in that upper layer. That upper layer is well mixed, as we saw, which makes it smaller still. So it's about 100 times smaller than the mesoscale, the submesoscale. Both of those, though, feel the rotation of the Earth. The Rossby number for the mesoscale is about 0.1, which means the rotation is dominant. For the submesoscale, it's about 1, which means that advection and rotation of the Earth are about equally balanced. And then the boundary layer turbulence is smaller still. And it's the part where it starts to become 3D. That's where the Richardson number reaches 1 or a quarter. And when you're at that scale, you can overturn just as easily as you can go sideways. And so it's a three-dimensional, the boundary layer turbulence becomes three-dimensional. Yep. So this has been tried many times. Usually when you look into the details, there's a numerical dissipation that actually is an equivalent or an, so you could do particle and cell, say, style, and then the merger rule and the split rule actually ends up being the same thing. Sure, we should talk about that later. Yeah, this is the standard piece. It would be lovely if there were clever ways around this. As I said, cleverness is the part that's in short supply. Okay. All right, so here are the Navier Stokes plus equations. So Navier Stokes up here, plus temperature, plus salinity, plus the equation of state. Okay, so let's count the variables we need to have. This is the equation for mass. It's got one new variable, density, and then it's got 3 velocities. So we need 3 equations for velocities. We've got 3 different velocities. So we've got 4 equations, 1, 2, 3, 4 unknowns. Oh, but now there's pressure, 5 unknowns. We need another equation. Okay, what about temperature? Well, temperature, boop, that gives us something about pressure, but the temperature, if we've added in a temperature equation, so now we have pressure here as well, we actually don't know the relationship between pressure, temperature, and density. So we're still missing a relationship. So we need salinity, which also depends on density. And then if you've been counting carefully, this equation of state, so we keep introducing one equation and one unknown, one equation and one unknown, 3 equations, 3 unknowns, one equation, one unknown, plus there's pressure. So we need one more to take care of the pressure, which is the thermodynamic relationship. So this is complicated. And there are all kinds of crazy things like the heat flux and the friction heat and the mixing heat, which are these interactions between molecular and like solar radiation, all kinds of fun things happening in the subgrid part. None of this is possible to resolve on a global scale, even remotely, but it's fun that you can at least write them down. Okay, but, oh, and I think I put this in the wrong place. Let me zoom back. So those equations apply over this whole domain. We just can't afford to simulate them. So if I pick a length scale, whatever, and I say, this is my grid, this is my box, what is the limiting factor for the time step I can take? What's the CFL, Courant, Friedrichs-Levy thing that limits me? It's on this diagram. It's the thing at the bottom. It's the thing with the fastest time scale for that length scale, which is always the sound waves. And this, in the sound waves in the ocean go very, very fast. In fact, they never really get close to anything else, which means that it's not going to be easy to scatter sound waves into some other phenomenon, which means that they're pretty much just on their own. So we could try and filter them out. If we did filter them out, we would gain this much, you know, which looks small, but it's actually about an order of magnitude larger time steps for the same set of simulation. I'm saying that sound waves don't couple strongly with the rest of it, so maybe we can filter them out without messing up anything we care about. They don't couple. They don't have an overlap in space-time, so there's not, at least not a linear coupling opportunity from a scattering style process. Okay, oh, sorry. Exciting, this is, well, anyway, I can explain why that is split. Yeah, well, anyway, all right. That's a long story about history of Brown and what Unsager was like that I'm going to skip for time. Okay, but we can talk about it later. Okay, so sound waves are killing us. So we have the CFL on 1,400 meters per second. A typical ocean velocity is like 1 meter a second. So it's 1,000 times smaller time step just because of that. So, and this is just going back through those. If you work out how big of a simulation you can do with direct numerical simulations now, it's about 1 cubic meter for a few seconds, which is cool if you're looking at sound waves, for example, but it's not so cool if you want to do climate change. Okay, so maybe we can filter out the sound waves, and that helps us a little. So how do we get sound waves? So we take the Navier Stokes equation. You basically look at the mass equation, and then we want to get rid of this divergence in velocity, so we combine it together with the velocity equation. So you take the divergence of this equation and the second time derivative of that equation, and you get something that looks like this, nice wave equation with the sound speed in it. There's a little bit of thermodynamics to find the sound speed from the thermodynamic properties. And then there's a lot of crazy stuff that goes along for the ride, which is like the stress tensor attenuating the sound waves. But forget all this stuff. They're the sound waves. And where do they come from? They come from this divergence right there. So this problem has been hanging around for a long time. So almost 125 years ago, Boussinesq said, well, the deal of it is it's a compression of that is the propagating mechanism of the sound wave. What if we limit the compression by separating the density variations into a space and time varying part and a background part? And in oceanography, sometimes we put a background part that's just in the vertical, which is kind of a convenience, but it doesn't, you can drop that if you don't care to. Then there's something called the buoyancy, which is the deviation from that background. And the buoyancy is like, am I anomalously light or anomalously dense? Am I tending to move up or tending to move down? So you put these definitions in, you asymptotically expand, you throw away everything that's not a derivative by just replacing a density with a constant density. All the places where you're taking a derivative of the density, you're very careful about. And the one other place, the gravitational term, needs to know about this buoyancy part, the deviation. That's the Boussinesq equations. So here they are. They're a little bit simpler. So we still have a temperature equation, which has got a whole lot of mess in it. We've got a salinity equation with a whole lot of mess in it. We've got a buoyancy, which now we need an equation of state for buoyancy, but that's doable. That's just like a conversion from one exchange to another. And then look what happened to the conservation of mass. It's become incompressible. So that's weird. We have density variations from place to place in the ocean. They're critically important. We don't get the driving power of gravity unless we keep the density variations, this buoyancy effect. But we also say the velocities are not allowed to converge. So how do we change the density without converging? We do it by sacrificing conservation of mass. So we are no longer conserving mass, we are conserving volume. But we know that that's a good approximation because things are only very, very slightly compressible. So we're keeping track of the density based on thermodynamics, not mass. And we're keeping track of mass by just saying we don't create or destroy volume. Then that takes care of the background part of the density. So in the ocean, that's a few percent error in conservation of mass. In the atmosphere, that would actually be a big problem because gases are more compressible than liquids. Surface gravity waves are still in here. So surface gravity waves don't, sound waves are not though. Surface gravity waves and internal gravity waves that are riding on the internal density variations are still here because this is still here. But the, yeah, I don't have the surface boundary conditions, which is another page of equations to write, but yes. Oh, but I should say, in one of the chapters that I included the ocean near surface layers, I go through all of the surface flux parameterizations as well. And you can see what those look like if you want to see those equations. There are a lot of them are drag law, but then there's also the heat flux, freshwater flux. How does it work? What happens if you couple an atmospheric boundary layer to an ocean boundary layer? What properties do they exchange? What do they conserve? That's all laid out in that chapter. Okay, so we got rid of the sound waves, but we have also changed the energy cycle. We can no longer convert internal energy to mechanical energy. So there are no heat engines. We've thrown them out. Is that a problem? So is the Earth system a heat engine? There's some nods. How does it work? Where's the energy? Where's the thermal energy coming from? Internal, from the sun, yeah. And then radiation back out to space. So we absorb more sun near the equator. We radiate more than we absorb near the poles. So there's this non-equilibrium thermodynamics because we've got different conditions at different latitudes. But the sun is heating stuff up at the equator and it's cooling stuff off. The radiation out back to space is cooling stuff off at the poles. That's really, really important for the atmosphere. The energy, kinetic energy of the atmosphere is a conversion from that internal energy that's put in there by the radiation. But the ocean actually doesn't receive hardly any energy that way. Most of its energy comes from winds blowing on the surface. So the atmosphere is the heat engine. The ocean is just responding, picking up some of that energy and using it to move stuff around. So the ocean's energy cycle is largely mechanical. If that wind effect mixes stuff, it puts potential energy into the ocean. If that wind effect pushes stuff and accelerates currents, it's putting kinetic energy into the ocean. And the transfer between the mechanical parts, the potential energy and the kinetic energy, is what the ocean dynamics is all about. So we're going to talk next time about how to do those budgets and how to do them in spectral and structure function and Reynolds average form. So you'll have a better handle on how those work. So that's maybe not the worst thing in the world. You can, of course, go back and use a non-Boussinesque ocean model, which is more expensive, and see how bad it is. It doesn't change anything, so that's fine. Okay, we also lose the ability to directly simulate sea level rise. Because remember I said when ice on land melts, you add mass to the ocean. Wait a minute, we need to convert between mass of the ocean and the volume of the ocean to figure out how the sea level rises, right? So this can be done diagnostically, but we're no longer directly simulating the ingredients of sea level. You have to do a diagnostic calculation, remembering this whole Boussinesque approximation. And you could take an intermediate step, which is what they actually do in atmospheric models. They don't use the full Navier Stokes either. They do the anelastic approximation, which is like it damps out sound waves in a different way. You can do that, and that actually can be done in the ocean pretty well. It's not quite as efficient, but it's something else you could do. Okay, so now let's jump back to our equation set. So now we have the equations. These are the Boussinesque equations. And now I have anticipated that we're going to talk about scales and what happens at different scales. So I've used a dimensionless form of them. So here's our Rossby number popping back. Here's our Froude number, which is closely related to the Richardson number. This is either you can think of it as the velocity over the wave speed, or you can think of it as like a Richardson number, 1 over a Richardson number. If the Froude number is small, the Richardson number is large. So it means when this is small, it means very, very stratified. When it's big, it means not so stratified. We've got the Pecquelets over here, we've got the Reynolds over here, and we've got aspect ratio hanging around in a few places. Okay. And then I've highlighted in under brackets, this is the geostrophic balance, which is where pressure is balanced by the Coriolis force. And for those of you who are physicists, just everybody in the room, you're saying, but the Coriolis force isn't a real force. You can't balance that against something real like the pressure gradient. It actually does do that. If you'd like instead to simulate the oceans where the continents and the boundaries are moving around at 1,000 kilometers an hour, you're welcome. So you're looking for a 1 meter per second current with boundaries moving at 1,000 kilometers an hour, which is a little bit tricky. Or you can go into the rotating frame and just deal with this funny force, which is not that big of a deal, actually, after you get used to it. Okay, so that's the primary balance for large scale motion. And what it means is that when you have a high pressure, the high pressure stuff doesn't flow away from the high pressure, it goes around and around it. When you have a low pressure, things go around and around it. So a hurricane is a big low pressure system and stuff goes around and around it, counterclockwise in the northern hemisphere, clockwise in the southern hemisphere, in order to balance these two pieces. Okay, hydrostatic balance. So throws away the acceleration in the vertical direction. And there's a big complicated mess of things on there. Okay, so which additional approximations can we make from this equation set at those different scales, mesoscale, submesoscale, and boundary layer turbulence scale? We've already made boost and S, so we've filtered sound waves, we've gotten out of that. What can we do? Okay, so let's think a little bit about the mesoscale. So the mesoscale has a small Rossby number, it has a very large Richardson number, and it has a small Froude number. It extends over the full depth, and the dominant process is that eddies are straining and producing fronts. The length scales are roughly 100 kilometers, time scales are roughly months. So this is where we sit. These are two satellite images of the mesoscale. This big eddy is a mesoscale eddy. Here's the length scale, that's 100 kilometers there. And these are big eddies here, same length scale as there. I made the figures the right size. This is in sea surface temperature over here. So eddies tend to be warm core or cold core, which is kind of interesting. This is actually false color. So this is the color spectrum from blue to green, expanded out so that our eyes can perceive it the way that, like, I don't know, a seabird or somebody who is really interested in seeing subtle variations in water types. So these colors represent things like temperature change, amount of turbidity, critters living in the ocean. What else influences this? Salinity a little bit, actually. So this shows the structures that are underneath and stirring up that complicated water types very well. So you can see the mesoscale eddies there. This is the Tasman Sea, and this is the North Pacific. And so this eddy looks like it's spinning that way. So is it high pressure or low pressure? You can puzzle that for a moment. Okay. So if you zoom out, we actually can observe the sea surface height variation. So the sea surface goes up and down with these eddies because they have high pressure or low pressure in their middle. So the sea surface is responding to that. And so you can do that, and then you can convert from that into a velocity scale through the geostrophic balance. And this is a log scale, so 5 orders of magnitude in kinetic energy. And you see their eddies everywhere. They have a weird tendency to drift westward, you may notice. And that's because they're not really just a turbulent vortex. They are linked to the Rossby wave characteristics. They're sitting on that space-time diagram right near Rossby waves. So you might think of them as nonlinear Rossby waves as opposed to vortices like you would think of small-scale vortices. Their dynamics are a little bit balanced that way. There also is a tendency for them to be attracted or repelled from the pole, where cyclones are attracting cyclones and anticyclones are repelling anticyclones, and the poles are kind of the mother cyclone and anticyclone. Those kind of dynamics are also at play. And then there's something really weird happening at the equator. There's all kinds of energy and it's like sloshing back and forth. Does anybody know what that is? They are topological waves. There are things like El Nino, things like La Nina, but also at the equator, the rotation axis of the Earth is perpendicular to the vertical. So there's a very weak Coriolis effect, or a very different Coriolis effect, because it's not affecting the vertical vorticity, it's affecting the horizontal vorticity. And so on Jupiter and other planets, Keith can tell us more about this, that it gets interestingly different at the equator, but in our oceans, it's a really different kind of thing. And so you can kind of neglect that geostrophic balance there and go back to regular old, push something and it goes the same direction you expect it to go. Yeah, so so the Rossby waves, when they are large in scale, they transport energy westward. And when they are small in scale, they transport energy eastward, but their phase velocity is still westward. So the energy is going in all different directions, but these small scale phases are going westward, which is a sign that at least on that scale, it's actually sending energy eastward. Yeah, These are fun waves. Okay. I don't remember why I have that in there. I was going to jump to that, maybe to say just we're in trouble about the resolution, but I think we made that point clearly enough already. Okay, so here are our numbers extracted for the mesoscale, Rossby, Richards, and Froude. So what can I do to those equations? Here's my Rossby number. It's handling all the advection terms, vertical and horizontal, and the convection terms. It's also over here on the stress tensor. And there's a Reynolds number, which is huge, absolutely enormous over here. So throw out viscosity, if we can, up to numerics. What about this part of the equation? Yeah, we could drop the advection and just keep geostrophic balance. Cool. Come back to that in a second. Okay, what about this equation? This is our vertical momentum equation. There's a Froude squared over here. There's a Froude squared over there. There's a Reynolds over here. Definitely drop that one. Froude squared. Froude's like, that's like 1 over 10,000. Drop all that. Hydrostatic balance is also okay. Down here, we don't get a whole lot of bang for our buck except for throwing away the viscous terms, but we knew we were going to do that anyway. And this is a really interesting one. So the scaling for vertical velocity gradient versus horizontal velocity gradient is kind of hard to work out for geophysical motions, but Jim McWilliams did this nice, clever trick to set it up this way. And so if the Rossby number is large, this scales like the Froude number squared. This is basically vertical velocity is limited by stratification. If the Rossby number is small, then it's limited by Rossby number times a Berger number factor. What's the Berger number for the mesoscale? That's the deformation radius versus the size of the feature. It's about 1. They're about the same size as the instabilities that cause them. So that's order 1. So Rossby number is small. So if Rossby number is small, epsilon is small, we get a divergenceless horizontal motion. So that's really weird. But that's the reason why eddies are there with this high pressure sitting in the middle. It doesn't just diverge away and spread itself out. It just goes around and around and around. That's exactly what it does. It doesn't diverge or converge into a high or low pressure. It just goes around and around and around. So those are the essential features of what's called the quasi-geostrophic theory. The only real wrinkle that goes with it is, how do you solve for velocity when you threw away the part that has DDT of velocity? So velocity suddenly become a diagnostic variable. But velocity is needed in order to calculate all this salinity and temperature transport. So there's a very weird set of equations based on potential vorticity dynamics, which we're not going to talk about, but there is a way to make a closed set of meaningful equations. Again, Keith's the guy to talk to about that. And there are multiple versions. Okay. So, but there are problems with quasi-geostrophy from the climate change perspective. So it might be cool if we're just looking at mesoscale eddies, but if we're thinking about climate change, we might not want to use those even for the scales where they are asymptotically justified. And let's see what that is. So it's a great toy model. It was really crucial in the early days of numerical weather because it not only filters sound waves, it also filters gravity waves and internal gravity waves. So you remove everything that's fast and your time steps could be like a week, not half an hour. So that makes your model really cheap. But it also requires the oversimplification of stratification. It tends to be spatially uniform in that fancy game I was telling you about how to make a solvable set of equations, which makes it unsuitable for climate because we really need the difference between the tropical stratification and the subtropical stratification and the Arctic stratification. Changes among those might be the biggest climate change signal we should be worried about from an ocean perspective. Like, is the ocean taking up heat in some part of the planet where it's not elsewhere? That uniform stratification is not a good way to simulate that. And then finally, the QG velocities are horizontally divergenceless, as we did discuss. And we're anticipating talking about the submesoscale now, but I'm going to watch this. We're going to watch this movie a couple times because it's completely insane. All right, so I talked about the BP funding. One of the things that we did was we went out and put GPS tracked drifters into the ocean, like 1,000 of them, so that we could, biodegradable ones, so that we could see what happens to them. You know, simulating oil by just putting particles that we could track, and we could capture them, we could release them, we could put them in different kinds of features, we could see what they were doing, talk about their statistics, which I'll talk about tomorrow. But something really surprising happened. So what would you expect if you just put a bunch of things in the ocean? What are they going to do? They're going to like Brownian motion. They're just going to wander away, right? Okay, this particular release did not do that. Watch the pink drifters. So this is a little bit after the initial pattern that they put that was kind of like a cloverleaf pattern. They just were driving the boat, assembling these things and throwing them out as fast as they could. This is in the Gulf of Mexico, right near the Deepwater Horizon spill location. So look at that. Watch what the pink ones are doing. They're going down the plug hole. They're all converging, and these don't sink, of course. They're buoyant drifters, but they all went into the same feature, which means that there was an enormous vertical velocity sucking everything down and going down. And so the seawater was not converging in 3D, but it was surely converging in 2D and going down. This kind of a process where you see heavy water next to light water, a front. It's actually a pattern of a couple of fronts intersecting that does this. And the heavy water moves into the front and then goes down, collecting all of those particles right at that interface. So we probably shouldn't use a horizontally non-divergent velocity field if we want to get this effect. This is quite clearly horizontally divergent. So this is really a submesoscale. These are down here in kilometers. So this was about a 20-kilometer deployment, and it collapses into within 100 meters of each other, which is kind of insane, but that was what happened. But so we might be a little worried about quasi-geostrophy for that from the mesoscale perspective. It turns out there is a little divergence, but it has only to do with the different Coriolis parameter at different latitudes in QG theory. So anyway, okay. Oh, do I have this? Here's another natural example of convergence into frontal properties. This is sea ice in the marginal ice zone. So this is kind of slushy ice that forms. And you can tell me where the eddies are, because look, the sea ice is converging into those same features, the fronts and the little eddies, which are an anomaly in density and anomaly in velocity. And now, what does sea ice do to the sun? It's really reflective, it's white. The ocean is really absorptive. So solar radiation is now not reaching through this ice onto those cold places below, but it is reaching through onto these warm places next door. There's also air-sea exchanges, which are damped by sea ice. So there's a major thermodynamic feedback from these features grabbing the sea ice and organizing it in a way that correlates with temperature, which is extremely complicated. So this is something we would like to do, which we still don't know how to do. Okay, so in sum, the mesoscale, hydrostatic is okay, but not quasi-geostrophic. Okay, so what about the submesoscale? So the submesoscale, we jump down another set of scales. I have these same two pictures, but now I don't want you to look at the big eddies. I want you to look at the little eddies. Those are the submesoscale eddies. And they're about 10 kilometers in size, 1 to 10 kilometers. They're smaller. And if we had a vertical profile of them, we would know that they were only in that upper ocean part, which we know from simulations with a mixed layer and below. The submesoscale doesn't survive into the stratified layer, but it tends to dominate these little eddies that form on, this is warm to cold water that's evolving, making little submesoscale eddies that have a structure like that. Okay. So what about the submesoscale? We look back at our equations. Oops, I didn't do that convenient one, so we have to look. So the submesoscale, they're smaller, but they have almost the same velocity as the mesoscale. So their Rossby number is about 1. So they rotate about once per day. Their Richardson number, they're trapped up in that boundary layer, and that boundary layer is well mixed every night. So it's a low Richardson. it's getting mixed up all the time. It doesn't have much stratification. So the Richardson number might be order 1. It could be as small as a quarter. It could be up to, up to 1. It could be maybe a handful, but not far from 1. And similarly, the Froude number is going to be about order 1. So these are turbulent features, but they have the same propagation speed as the internal waves that are also in the same environment. So we can't easily distinguish when we see variability, whether it's an internal wave from a tide or submesoscale eddy or what. It's all mixed together. And so this is starting to sound like there is no asymptotic theory allowed. Let's look. All right, so this is order 1, so there's nothing we can do. Got to keep the whole equation. This is still small, so we can parameterize viscous effects somehow. This is order 1. This Froude number part is order 1. So this Froude number part is order 1. And then this Froude number, this is kind of order 1. So it's right on the touch line between theirs, but basically it means epsilon is order 1. So that big vertical velocity that sucked all those drifters into one spot could be almost as big or same size as asymptotically the horizontal velocities of the submesoscale. So we almost can't simplify anything, except now notice that we still have an aspect ratio here that we haven't talked about at all. It turns out that those submesoscale eddies, they're trapped in the boundary layer, which is about maybe 50 meters deep. They're still 1 to 10 kilometers wide. So they're still wide and shallow. So we actually can preserve the hydrostatic relationship, not on the basis of the Froude number, because it's weakly stratified there, but on the basis of the aspect ratio of those motions. So we can still use hydrostatic Boussinesque for this scale, but we definitely can't use geostrophy because that term is just as big as this term. Okay. So Rossby-Richardson 1, submesoscale is the most active in the surface and bottom boundary layers, just not deep enough to have the order 1 aspect ratio. So we keep hydrostatic. And now you might be saying, I keep telling you what scale these things are, and I have this like weird deformation radius and instability scale. How big is that scale? Why do I know that? Whatever. I know it because we know the full linear theory for the instabilities that cause both these mixed layer instabilities, these submesoscale eddies, and other classes of instability that happen in the submesoscale. And you can take observations and determine the scale at which those instabilities occur. So once we've got the hydrostatic Boussinesque equations, we then look for their linear instabilities. We apply them to this problem of the upper boundary layer. We take observations of the stratification, the velocity shear in the upper boundary layer, and make something like this. And so those eddies, how big are they? Well, they vary strongly with latitude, vary pretty strongly with season. So they're about a factor of 2 bigger in the winter than in the summer. And they're about a factor of 10 to 20 bigger near the equator than they are near the pole. And then this smaller set of symmetric instabilities, which is a smaller scale instability, which has different properties, it's about 10 meters to 2 kilometers. So this is kind of the smallest thing that we associate with the submesoscale. Okay, so submesoscale, we can still use the hydrostatic Boussinesque equations. We definitely should not use the quasi-geostrophic equations, and we know what the scales are. Yes, because we can't estimate the shear from satellites unless we have the geostrophic balance to help us. And so we just don't really have those measurements that we need. The F is too small, so we get into trouble. So we just choose not to do that rather than trying to. Oh, the way that we estimate it is different between these two. One of these is based off of a model, and one of these is based off of, this is kind of a hybrid of model and observations, and this is just pure observations. Yeah, well, they're both hybrids, but anyway, that's fine. Those are fun things to see. You can go check out these two papers to see how the technology behind figuring out how big these things are. Okay. All right. Hydrostatic is okay, geostrophic is out for the submesoscale. Okay, now, next scale down, last scale we're going to talk about today. How big are we? Okay. So this is actually the Deepwater Horizon spill. This is a satellite image, visible radiation. So oil, after it degrades in the sun, turns this kind of orangey color. And here's an airplane for scale. So what do you see when you look at this picture? You see, well, there are these big streaks. Why do we think they're big streaks? That's one question. There's this sunlight, which looks like there are waves perpendicular to the streaks. And so those are hints of the dynamics that are underlying this kind of clustering of the surface. That stuff is piling up in what are called windrows. They align in the direction of the wind and in the direction of wave propagation. And they're thought to be from something called Lagrangian turbulence, which is little vortices like this that form with, so this is the surface, this is the wind and wave direction, and they tend to go like this. And so at the surface, they have convergences and divergences alternating. And the convergence is where all the oil piles up. There are other kinds of helical vortices, kind of curvy stuff that you could also have. So it's not 100% sure that that's the kind of boundary layer turbulence that's doing this, but you certainly want to exclude that kind of boundary layer turbulence in analyzing this kind of an event. Okay, and, well, yeah. So how do we, so this is where, well, so I'll tell you a little bit about how this works, and I'll tell you a lot more about how we parameterize this kind of turbulence on Wednesday, and some of the scaling laws that go into this and where they come from. They basically derive from the Monin-Abakov similarity theory, which involves how the surface stress and surface heating and cooling compete to produce energy for this kind of vertical mixing. This wave-induced one requires you to also think a little bit about the waves. So I want to talk a little bit about the waves because it's a more interesting story about being careful about the equation set we choose than we have been so far. And so that's where I want to go, which is a little veer away from things. Okay, so there's something called the wave average Boussinesq equations, sometimes called the Craik-Leibovich equations. They've been used for simulations of Langmuir turbulence for about 20 years. But actually they're capable of doing much more stuff. So this is our first parameterization that we're going to discuss of an unresolved effect. And the unresolved effect are the effects of waves. So how do we do that? Well, first we want to know a little bit about waves. So waves at the beach tend to break a lot. Waves in the open ocean, which this is a beautiful example of, giving that ship a very hard time. You can wonder what platform they're sitting on that makes the platform is stable and the ship is not, which is interesting. But anyway, waves have a very broad spectrum of characteristics. So they have big swell waves, they have small wind waves. The swell and the wind could be propagating in different directions, but the wind waves tend to be propagating in the same direction as the wind. And one of the key things that they do is if you follow an orbit of them, so they are a solution, they are a non-divergent, irrotational solution to the Navier Stokes or the Boussinesq equations right near the surface. So you neither converge or diverge nor rotate on average in that fluid. But you can do that. There still isn't a non-trivial mode there because the surface goes up and down with it. So the surface boundary condition is changing, which allows you to get away from if you normally in a fluid with no boundaries, you couldn't say it's both curl-free and divergence-free. You would say there's no flow there. That's not true when you're at a boundary that can have a evanescent decay away from the boundary conditions, which is what these waves are. Okay, so anyway, the velocities that they tend to have, if you sit at a point and measure the velocity, it goes around in a circle around you. So the velocity is going like this, and there's no net velocity, there's no average. It just goes around and around and around. And it tends to be, for a non-hydrostatic version of this, it tends to be bigger at the surface and smaller as you go down with depth. The longer the wavelength, the slower that decay. So really long waves like tsunamis have pretty much the same orbital pattern at the surface and right near the bottom. But these kind of waves, the ocean might be a couple kilometers deep, and those are maybe 25 meters apart or something. So they're decaying over the first 100 meters or so pretty quickly, like this. So imagine Not if you're sitting there at an Eulerian location, measuring the velocity that goes by you, but you're measuring a Lagrangian trajectory. So this is an example of a Lagrangian trajectory. When I'm near the surface, I'm in this big orbital velocity. I'm going fast. And then I plunge down, riding along this. And now I'm down here with the slow velocities. And then I come back up for the next cycle, and I'm going in the fast, and then I'm going slow, and I'm going fast. So I actually don't go in a closed loop from a Lagrangian perspective. So the Lagrangian average velocity is not equal to the Eulerian average velocity. They are different from one another. The Lagrangian average velocity, the Eulerian average velocity, and the Stokes drift, which is this little extra bit you get at the top versus at the bottom because of that decay. So the Stokes drift is one really critical piece of how these waves work. And it's a really critical piece for interactions with turbulence because this has shear in it. You could conceivably take the Stokes drift and drive turbulence with it. Oh, and this is a little movie just showing you if you track particles in a wave solution. This is from Wikipedia. This is great. This is like one of the best animations of Wikipedia. I don't know who made it, but anyway, you can see what I mean by that Stokes drift is the drift, and it tends to be sheared faster near the surface than at the bottom. The drift speed, the drift speed, it's proportional to the third moment of energy. So it's not quite proportional. It's the 2/3 power of wave height. It's a funny transformation because it's got wavelengths in there as well, or frequencies, depending on how you think about it. Okay, so you take the Stokes advection. So one thing that the Stokes drift does is it pushes around particles. Cool. If I put vorticity in this fluid, it would also push vorticity. If I put energy, turbulent kinetic energy in the fluid, it would also shift the turbulent kinetic energy. It would strain out the turbulent kinetic energy and maybe affect the turbulence, make the turbulence more efficient, less efficient, right? These hunks of mass of water that are moving around are also on a rotating planet. So that Stokes drift also triggers a Coriolis response. So it's a moving particle on a rotating planet, so it also experiences a Coriolis force. So this is something you might want to think about. And then there's an obscure one called the Stokes shear force, which is closely related to the Stokes vortex force. But this basically means if you're going in the same direction as the waves, the wave-wave interaction averages out to push you downward. If you're going the opposite direction of the waves, the wave-wave interaction works out to lift you upward. So, and it's just a matter of going through, taking the wave solution as a small scale solution and thinking about the most dominant coupling terms to a larger scale hydrodynamic, Boussinesq equations. The linkages are these three terms in the equation set. So here's our hydrostatic Boussinesq equations, including those wave linkages. The yellow is the Lagrangian velocity, where it would have ordinarily been an Eulerian velocity. And this is the weakest coupling you could have between the waves and the Boussinesq system. So here's Lagrangian advection in the vertical equation, Lagrangian advection in the buoyancy. That's not so surprising. Here is the Lagrangian Coriolis force. Cool. So there's also Stokes plus Eulerian Coriolis. That's not surprising. Then here's that weird Stokes shear force. Okay, so we're going to come back to this in a second. There's an epsilon in front. This is now dimensionless equation set again. There's no epsilon in front of this. There's nothing different about the Eulerian and the Stokes velocity from the Coriolis perspective. They feel it the same way. The advection by Lagrangian versus Eulerian, there's no scale factor there. They are the same, one is smaller than the other maybe, but there's no front part. You'll also notice that there's not Lagrangian advecting Lagrangian. This is one of the weird things about the way these asymptotics work between the two scales, which is a whole longer conversation. Okay, so what is this epsilon parameter? Well, it's the Stokes velocity, the height of the motion you're thinking about, that decay depth of that Stokes drift, and then it's got Coriolis in there. and it's got a horizontal length scale. So it looks a little bit like a Rossby number for the Stokes drift times a factor, which is the height of the motion divided by the height of the Stokes drift. And this is a small number. The Stokes drift is actually usually weaker than the Eulerian velocity. This is a really big number. It's not clear what the product of that number is. So that's what we want to think about a little bit. Okay, so this is where we did that big simulation. And I'll say that this was not a small simulation. This is a 300 teragrid simulation. So it's a lot, whatever, hundreds of graduate students garnering their resources together to do one simulation, kind of simulation. And this is, remember, this is the one that we zoomed into, and we saw these turbulent, oops, I didn't even have the zoom move again, but we zoomed in and we saw those Langmuir cells and the fronts interacting. And so these were the equations that we were solving for that equation set. They included the Stokes drift, included those forces. And we knew that this Stokes shear force was going to do something special. If the motion, so it was going to do this, there was going to be Stokes advection. It was going to do this, there would be Stokes Coriolis. We knew all those pieces. But what about this part? So the Stokes shear force is when the Lagrangian velocity, here's the Einstein summation, is in the same direction as the vertical shear of the Stokes velocity. So the Stokes velocity is going in the same direction as the waves. The Lagrangian, if there was a little velocity, like this indicates, was also going in the same direction as the waves. This would be a positive thing. And what does it do? It pushes downward. It looks like a buoyancy. So buoyancy, you know, if buoyancy is negative, stuff sinks. Buoyancy is positive, stuff floats. This thing rides right next to buoyancy in the equation set. So it says, if there's a velocity in this direction, and if there's waves going that way, you would push downward right here in the middle of that vortex that's the convergence zone. Yep. Yeah. They also do that. Even though that's not included in what we're talking about now, they do. The frequently buoyant stuff gets kind of sucked down here and then pops back up, and it does suppression of turbulence. But the opposite way, it's not because dense stuff is being lifted up into the air, it's because buoyant stuff is being pushed down into the water. So it does actually suppress. There is a bubble correlation, which is kind of fun. It reduces the efficiency of this.
Trying to understand what's driving
What's driving what?
driving
So we have a random velocity field on the surface. We've got some kind of submesoscale or boundary layer turbulence. If you happen to have a velocity that's going in the same direction as the waves that are driven by the wind separately, this is a Stokes drift. This term kicks on and says, push you down right at that spot. And so this is just a different way. Oh, I was going to actually do the vorticity explanation too, but this is just a different diagram showing the same thing. There's a little Stokes shear force that goes downward whenever you're moving, or your particle moving in the direction of the waves, which pushes you down. And then we know that the velocity here has to be weaker than there because now we're going back up. So the Stokes shear force is still downward, but it's not downward as much as it is over there. So this is the energy creating phenomenon for these guys. So there's a downward force for down flow Stokes drift. Okay, and so you can combine the three of these together and call it wavy hydrostatic, because it's still kind of hydrostatic. We're not dealing with these terms, but we do have something that's competing with buoyancy, push stuff down or lift stuff up. So that's exactly it. It's extracting some of its energy from the surface turbulence, that's the Lagrangian flow, and some of its energy from the Stokes drift. It has multiple sources of energy. So this was the question we didn't know. The Monin-Abakoff theory doesn't actually predict this. And so this is a deviation away from the Monin-Abakoff similarity. So what I'll talk about on Wednesday is the quantification of how much extra mixing this does and whether that is important for climate. But it's not the first order effect. The first order effect is wind driven and cooling at the surface driven mixing. But it enhances both of those by about a factor of 2 in vertical velocity units. Okay, so I'm gonna skip over this. Okay, so now we have this epsilon parameter that says how much does it compete? And we have the Rossby number. And so the Rossby number tells us how ageostrophic the flow is. And I can't tell you how many GFD or physics talks I've been to where people say, oh, here's my Rossby number, and I'm going to talk about the nonlinear effects because that's what brings in the advection term, because my Rossby number is large and boundary currents and eddies and all kinds of things, right? So it's hard to estimate this thing directly, but it's pretty easy to estimate the ratio of these things directly. So I can say how big of a term is that Stokes shear force in the vertical momentum equation versus how big of a term are the ageostrophic effects in the horizontal momentum equation. So this thing we've said is really important for the submesoscale. It's what leads to that convergence and the suck down the plug hole effect. What about this? Now we know when we get to the Langmuir scale, this thing's going to be really big. This is what's driving those Langmuir cells. That's the source of energy. You know, that scale's the source of energy. That's not surprising. What about on bigger scales? So this is where that 300 teragrid simulation pays off. But here's the scale estimate. So I take the ratio of epsilon to Rossby, and you can estimate all these parameters from observations. And look, the numbers are like 10. This thing is 10 times more important than this thing. But this thing is 95% of the discussions in oceanographic conferences. We don't talk about this thing at all. So what does this thing talk about? It says, this is actually an estimate for kind of mesoscale-ish horizontal length scales, because that's the data sets that went into it. So it says that vertical acceleration, we should always be in the wavy hydrostatic limit, not just at the Langmuir turbulence scale. This thing is not, if this is bigger than 1, that Stokes shear force is bigger than buoyancy. If it's small, you might say, oh, it's just a second order correction. But I'm telling you, it's bigger than the Rossby number, which is a correction that we're keeping. We didn't allow ourselves to go into quasi-geostrophy because of these finite Rossby things like the going down the plug hole part. So what does this do? So now we go back to that simulation, and we ran 2 versions of that simulation, one including the Stokes drift and one not including the Stokes drift. This is the one including the Stokes drift, and this is the one with just wind. And so this is showing vertical vorticity scaled by the Coriolis parameter, but basically white next to black here is a jet. It's a thing that's got 2 signs of vorticity. It's got a strong central flow. This is where I showed this, and Jim McWilliams, with his clever way, said only a trained oceanographer can see the difference between these 2 panels. They basically just look like 2 turbulent flows. But would you say, first of all, that those jet features are stronger over here on the left? Some nods. Would you say that they are sharper when the white is on the left side of the wind and the black is on the right side of the wind? Not so much this one, right, where it would have been going the other direction. So if you test these 2, this is actually fairly isotropic about what the directionality of those strong frontal features are. Over here, the fronts are extremely strong, but only when they're pointing in the same direction as the waves. So these are submesoscale features so now we can go back to this big movie and just zoom into different little boxes. What do we zoom in over here? Well, there are no fronts. That's just Langmuir. Over here, no fronts, just Langmuir. But over here, we get a very weak front, and it's going sideways. Over here, we get a really strong front, and it's going the same direction as the Stokes drift. Over here, we have a really strong front, same direction as the Stokes drift. Up here, we have a weak front. It's trying to go the other way, and it kind of wimps out. So to zoom in on two of those boxes again, here's the wind and wave direction. Here's the frontal flow, and it has a big alignment along the direction of the waves. So it's experiencing a Stokes shear force. It has a flow that projects onto the wave direction, so it's getting pushed downward. And remember, I said that's the way those fronts work. They converge, they put dense stuff down, so that convergence is actually being accelerated by the surface gravity waves. Whereas if you're going in a different direction, you don't get that acceleration. Here's a front going sideways. It would have no Stokes shear force because it's perpendicular. The Lagrangian velocity is perpendicular to the Stokes shear direction. Okay, so the point here is this thing doesn't only matter for Langmuir, it also matters for the submesoscale in the same way. And I think I have one frontal example to show, then we're done. So here's a strong front. It happens to be going in the same direction as the waves. We zoom into a box like that to do some statistics. That's its horizontal velocity. There, it's a very sharp temperature front. Here's the vertical velocity. And you can just see the feature that its vertical velocity is way stronger than all these Langmuir cells around it because it's a really strong front heading right along those waves and getting the acceleration. If you put surface drifters in that model, they all end up in the front. And looking from the side, we see exactly, here's the warm side of the front, the cold side of the front, and there's associated with this an overturning that's sharpening that front. Here's the stream function for that overturning. And you see there's a little kink as you go around. That kink is right at that location there, which is exactly where the downward Stokes force is. So about 44% of, oh, I've forgotten how to read this table. Well, I won't tell you. Anyway, at leading order, the angular momentum associated with that frontal sharpening, about a third of it is coming from the surface gravity waves, which you never would have put surface gravity waves into submesoscale features, big fronts, because why would they have anything to do with each other? It's only when you go through the asymptotics and look at how that epsilon factor is small, but it's bigger than other things you were worried about in that equation set. So it rivals those kind of convergent flow dynamics. So our parameterization of the coupling between surface gravity waves and turbulence actually could be a parameterization for the coupling between surface gravity waves and submesoscales as well. The hydrostatic Boussinesq equations, the wave average version, can handle that whole system. All right, that's all I wanted to say. Thank you.
A few more questions before we head off for lunch, and then rest, and then the lecture at 7, as I keep reminding. Go ahead.
Yeah, here's Steve. So there are observations of, well, I can tell the relative importance of their ratio. So the ratio is the simple thing to calculate. Let me go back so you can stare at that figure while I'm saying it. Where'd it go? I've gone too far. I've been way too far. Sorry, while I'm on this tour. I will say, so their ratio basically becomes the ratio of the depth of the velocity shear versus the Stokes shear depth. And that's something you know if you just know the wave properties. So we actually use a wave model. And then the other, so the ratio of this to this, the Coriolis and the horizontal length scale cancel out. So I don't have to tell you what the horizontal length scale is because it's the same as this one. But the little h over h, this is the depth of the current. This is the depth of the Stokes. This is a big number. So this is like typically, we use the mixed layer depth for this one. So it's a submesoscale shear we're thinking about. And this, we use the wave properties. In the Stokes drift, we have the wave properties that are giving this a Stokes drift. And then the velocity field we took from Aviso, so from satellite measurements. Yeah. Oh. That was actually, yes, we're simulating that, but we didn't we didn't actually couple to the mesoscale because that would have been a 300,000 graduate student simulation. Anyway, we just put an initial cold, warm, cold initial condition in. So we put potential energy into the submesoscale to begin with, and then we simulate its evolution from there. So it's a spin down of potential energy problem. Mm-hmm. That's true. So the mesoscale eddies don't actually need to converge to bring the temperatures together. So in fact, it's usually just strain that's stretching, that's making these fronts form in the horizontal. And then that frontal overturning responds to that in a much more complicated process called frontogenesis, where once you get warm next to cold, it tends to self-reinforce with the overturning circulation. And so that frontogenesis process makes the fronts even stronger. That second part does involve an geostrophic convergence process, but the first part doesn't have to. Yes, it's a time, it's the Lagrange, you're basically making the difference between the Lagrangian velocity and the Eulerian velocity.
So then you take this kind of, I guess, like, I think of this as like non-linear frequency, but if you're converting some frequency omega down to the DC component using this non-linear convection to get this Stokes drift. And then you kind of put this back into the equation to get the Stokes shear force. So I was just curious, like, why is this the right thing to do?
Right.
Like other harmonics, for example.
Absolutely, that's a great question. So we're in the scenario where we're imagining the waves are fast and then the turbulence is slow. So the time scale of waves is about 10 seconds and the time scale of that boundary layer turbulence is about 10 minutes to an hour. And so it's a time scale separation multi-scale problem. The Stokes drift is the residual in the Lagrangian velocity of a long time average over many wave periods. So it's the thing that in time, in spatiotemporal terms, matches up to the turbulence and causes a strong coupling. So it's the reason why that term jumps across scales is because it's a residual over a long time. Whereas the orbital velocity has a very, very weak coupling to the turbulence because it's just totally separate in frequency space. Stokes drift is like 2%, normally 2% of the wind speed is what you say is the Stokes drift. So it's like a couple centimeters a second, and then a typical submesoscale current might be 10 centimeters a second, and the Lagrangian, the convergences in a Langmuir cell might be 10 centimeters a second.
Gulf of Mexico observation, the drifters. Did you know you were going to get that result, or was that
No,
serendipity?
they had no idea. They go out and they do these clover leaf patterns, and it's like we were looking for the statistics. I'm going to talk more about the statistics tomorrow. We wanted to calculate things like the structure function of the separation and between those drifters, and we thought that was going to be all we were going to see was kind of statistical stuff. But then once you go out and you put things in, features pop out, and they're so dramatic that you want to tell a story about the feature instead. So they weren't feature hunting in that, but it turned out there was a beautiful feature just waiting to be found.
Any other questions?
So the Ekman layer is underlying all of this. So the reason why this drifts that way is the Ekman transport. So this turbulence that's mixing here is actually taking the stress at the surface, the momentum input, and mixing it vertically, but it can't do it cleanly. It actually gets interrupted by the Coriolis force as it tries to do that. So it gets a rotating profile, that Ekman layer profile. So this is not a linear Ekman layer like you learned maybe in Oceanography 101. This is a fully turbulent Ekman layer, but that's the reason why this is drifting sideways.
I think everybody's hungry.
Yes.